So now the next thing, we have to start with the logic gates. So what is this logic gates? So if you have seen that the latest technology we are using, say for example computers, so there is one chip which we have discussed. So there are millions of, you can say now, that gates are there. So gates which consist of, or which are made from your transistor, and they can operate as a on or off. So within 1 second they can obtain, or you can just operate n number of times. So they are just continuously doing that on and off functions. So that is nothing but what your gates consist of. So which is a transistor circuit, and which will make, either it will act as a on, or either it will make as a off. So before that, we just see the difference between this analog signal and digital signal. So all this is nothing but, it is a digital world. So we are just talking about everything is digital. But what do you mean by exactly digital? So when we are just thinking about the digital signal, there are only two possibilities. Either you can do it, or either you can't do it. It's not like that. So it's not in between that. So either, so you have to just make it who can, that is just you have to do that. So this is analog signal and digital signal. So a continuous signal. Now analog signal, it can take any value, so which is varying continuously with respective time, whereas the digital signal, you can say that it just takes some predefined values itself. So this is how you can show that. So this is the analog signal, V is equals to V naught sine omega t, and this is its amplitude, how you can represent it. Then in case of digital signal, so this is how you can represent those digital signals. Okay, so that we just define in terms of ones and zeros. So that logic 0 is nothing but 0 volt, logic 1 is nothing but 5 volt. Either you can just change it also, it is not like that. So either you can take -5 plus 5, so that's up to you. So that means we just define according to our given specification, but generally we just talk logic 0, we defined it as a 0 volt, and logic 1 as a 5 volt. In case of this analog signal, so V is equals to V naught sine omega t. That V naught, we can say, is the maximum value. Omega is nothing but your angular frequency. So this digital circuit, definitely it is an electronic switch which operates in two states that I told you, either it is on or off. Again, we have just discussed that. So the on state is represented by one of the, that is a voltage level, and off state is also represented by another voltage level. So that either you can take the same thing I told you, either logic 0, 0 volt, logic 1, that is a 5 volt, but it is not necessary that you just take those two values. So you can define it for any other values also. So this is also called as a binary number system, which has only two digits, 0 and 1. So this is a binary number system, so that we just call as, so that is on and off represented by digit 1 and digit 0 respectively. So what is the binary equivalence of your digital or that decimal number? So the decimal number has the base 10 because of 10 digits, that is 0 to 9 used in the system. But then in case of your binary system, it is having only base 2. So either you can represent that is a 0 and 1. Okay, so this is how we can just represent that is in the system. Fine. So that is what about your, so this is how we just going to represent it. So this is your 8, then 9, 10, 11, 12, 13, 14, 15. So this is how all the numbers you can represent with the help of this your binary equivalence of decimal number. So this is how, so the various decimal number you can represent with the help of this binary. Okay, now what is this Boolean algebra? So this Boolean algebra, you have to just do those different operations on those logic 0 and logic 1. So that is nothing but, so what we will say that it is a Boolean algebra. So let's say this is a circuit which consists of two switches, and this is a bulb that has been applied across this your battery also. So now let's see the first, that is a Boolean operation, that is a OR operation, which is denoted by your plus. Again, then next we will say that, so if the Boolean expression is given by a plus b, so what is the condition over here? So under what condition you can say that, so this bulb will glow. Yeah, so it is equivalent to Y equals to A or B, that is why it's called as a, yeah, so that means even one of the switch is open, still the bulb will glow. Yeah, still you can say that the bulb is going to glow over here. Yeah, and the same thing you can represent it, that switch A, if it is off, both the switch if it is off, yeah, so here you can say that, so even both the switches are off, bulb is off. Yeah, if one of them is on, so then definitely again you can say that, yeah, so again you can say that for particular case, so this is nothing but off on, then it will be on. Yeah, so this is how you can just define that your OR operation over here. So this is what we can say about the OR operation. So this is about your OR operation which we have seen. So the next one is the AND operation. So AND is operation is represented by Y is equals to A into B. A and B, these are the two inputs, so it might be logic 0, it might be logic 1, so that it reads as a Y equals A and B. Then again it means that if both A and B are true, then your Y is also true. So this is how you are going to show it now. So this is with the help of switch A, switch B, if both of them are open, yeah, so definitely, so this is how one of them is closed, one of them open, so this is how we can show the various cases. Yeah, so if both of them are off, then definitely the bulb will not glow, Y is equals to 0. If one of them is open, one of them is closed, still the circuit will not get closed, there will not be any flow of current, so the bulb is off, the current is going to flow or the output is 1 only when both A and B are closed, so both should be on. Yeah, so then your bulb Y is on. So this is how you can represent the truth table for this your AND operation. So similarly, NOT operation, it is represented by that OR of, that is NOT. Yeah, so it is a bar, you can say that it reads as a Y equals NOT of A. So it means that if A is true, then Y will be false. Yeah, so it is opposite to that of simply. Yeah, fine. So this is how we can say over here. Yeah, so here we are just closing the switch 1, so that makes the output 0. Yeah, and if it is on, then it will make the output off. Okay, so this is what we can say about those different gates. Now you can just, so there are fundamental, we are saying that 3 gates, OR, AND and NOT gate. Fine. So again we can just use the different combinations for them. So if there are, let's say, n inputs, then there will be n raised to 2 possible input combinations that you can consider. So for 4 input gates, so this is how you will get the 16 number of input combination. So what is this digital OR gate? So the same thing you can represent with the help of gates also. Yeah, so this is how we have just shown over here. So you have to just apply that input, yeah, and you can just represent with the help of your output that you are going to apply at the across the RL. Yeah, so even if one of them is closed circuit, there is a flow of current and you will get the output. Fine. So this is how you can just represent with the help of this gate. So this is OR gate. So the same thing which we have just discussed in terms of zeros and 1. Yeah, so this is again the circuit of your AND gate. Yeah, so the previous one, so this is what we talk about. Yeah, so this is what we talk about the OR gate. Yeah, so similarly you have to just talk about this AND gate. Yeah, so the AND gate which is represented by this table, and this one is the NOT gate where you will get the inverse output. Fine. So when we are just saying that when there is a high value of input current, obviously you can say that input voltage is high and the output voltage will be low. Okay, so that is what we will get in case of this digital NOT gate also. Fine. So this is one more circuit, that is a NOR gate. So that is a combination of your NOT and OR. So this is what we can say that. So definitely this is your OR. Yeah, so this is what we can say over here. So this is nothing but your OR, and that is the NOT gate, so which we connect over here, so that will give you the NOR gate. Yeah, so this is how you can represent. So this is your OR and then NOT, and then what you can say the operation for that. So we know for OR, yeah, so just take the inverse of that, so which will give you the NOR gate. So 0 0 0, that makes inverse 1, 0 1 1, inverse 0 1 0 1, inverse 1 1 1 0. So that is how you will get NOR gate for that particular case over here.